This is episode 21 of MATH1050 College Algebra for our television course. I'm Dennis Allison and I teach in the math department. We'll be looking at a review today of the chapter on logarithms and exponential functions. Let's go to our first list of review ideas. Number one, you want to be prepared to solve problems that are similar to those that we've just been discussing in class in the last few episodes, and those assigned for homework. Now, you know, occasionally there have been some problems that we didn't necessarily cover in our television course, but you'll find examples like those in the textbook. You want to make sure you know how to do those. One of the differences between this exam and the first two exams is you can use a calculator to solve certain problems. Those problems will be given to you separately on the test, so that you should be able to use your calculator to compute logarithmic values as we encounter them. You cannot use notes, and of course you cannot use your textbook. You'll be given some extra scratch paper with the exam, but you'll have to turn that in when you turn in your exam. And we encourage you to show all your work to justify your answers. Otherwise, if you have a wrong answer, you may lose full credit. Whereas if you show some work, then if we can find the mistake that you might make in that, then you can get partial credit. And we try to be fairly generous with the partial credit. Okay, let's look at the review ideas for episode 16. Now, in episode 16, we introduced exponential values and how to compute those with your calculator. Now, if we can come back to the green screen, let me just remind you that on your calculator, to find an exponential value, you'll either have a key that says y to the x, or it could say x to the y. This depends on the manufacturer of your calculator. Or another common exponential key is this little caret thing pointing up. And you enter the base, then you push this button, one of these buttons, and then you push your exponent afterwards, and then you hit the equal sign or the enter sign, and you'll get the exponential. So for example, if you want to say 2 to the third power, then you hit the equal sign, and it should say 8. Now, of course, the reason you hit the equal sign is because when you hit 3, when you push 3, your calculator doesn't know if you're pausing to enter 31, 2 to the 31 power, or if you're finished. So when you hit the equal sign or the enter sign, then the calculator knows that you're done. Okay, let's go back to episode 16 and look at the other items on that list. You should be able to sketch the fundamental exponential functions, and then in connection with that, you should be able to sketch transformations of those functions. And in each case, this should be done by plotting only the target points, not making a table of values. Why don't we take a few examples of those right here? Suppose that I wanted to graph the function f of x equals 4 to the x power. Then there were 3 target points that we associate with this exponential function. And let's see, let's just get our graph system, our coordinate system set up here. And the target points were, let's see, now at 0 we go up 1 unit. And if I go over 1 from the origin, then I should go up whatever the base is. So I go up 4. So I'm going up 4 right there. And if I go to the left 1, I go up the reciprocal of the base, 1/4. Now, you notice I'm doing this in a rather mechanical way, but I think all of these values make sense, because you see, when I choose x to be 0, when x is 0, I get 4 to the 0, or 1. When I choose x to be 1 right here, then when x is 1, 4 to the first power is 4, so I went up 4. And when x was negative 1, then the value there is 4 to the negative 1 power, and 4 to the negative 1 is 1/4. So we went up the reciprocal of the base. Now, on the basis of only those 3 target points, we can draw our exponential graph. But we have to know that there's a horizontal asymptote along the x-axis. And we have to know that there is no vertical asymptote, so I don't draw in any vertical dotted lines. So this is how we'd like for you to graph this function and not make a table of other values, but plot only these three points. Let's take one more example of an exponential function. And I'm going to try to hide it in a sort of a minimal way. Let's say we call this function g of x. And let's say this function is 3 to the negative x power. What is the effect of the negative in the exponent? What is that done to hide the exponential function? Jeff, what's another way you could write that?
1 over 3 to the x.
Or 1 over 3 to the x. Yeah, so this is actually 1/3 to the x. And you see, a lot of times students think that this graph is going to look like the one I just graphed before, where it goes up on the right-hand side. But actually, it's going to be going up on the left-hand side because the base is smaller than 1. The base that we choose, either 3 or 1/3, we always choose positive bases here. So you'll never see a base 0, or you'll never see a base that has a negative number in it. Okay, well, I want to graph the function 1/3 to the x power, or 3 to the negative x. And to do that, I'll plot 3 target points, just as before. And I'll plot them in the same way. That is, at 0, I'll go up 1. If I go over 1, I go up the base. Now, when I say the base, I mean the base in this expression, 1/3. And if I go to the negative, if I go over to -1, I go up the reciprocal of the base, and the reciprocal of 1/3 is 3, so I get a point at 3. And so this graph comes down and approaches the positive x-axis as a horizontal asymptote. Now you might say, well, Dennis, how are we supposed to know if 3 is the base or 1/3 is the base? Well, you see, a function is in standard form when it's written a to the x power, and this is where a is bigger than 0. So if there's a negative exponent here, I have to get it to the form a to the x, and then a is the base that I use when I'm plotting these points. Okay, now let's look at transformations of these functions. This is still in episode 16. And this time, I'm going to take the function f of x equals 2 times e to the x minus 1 minus 2. Now, I have 3 different transformations in this function, 3 different basic transformations. When I subtract 2 on the outside, that's going to lower the graph 2 units. And when I subtract 1 directly on the x, that's going to shift it to the right 1 unit. And when I multiply by 2, that's going to be a stretch. So it's going to double the altitude of the points, or stretch them away from the x-axis. Now, when I write 2e to the x minus 1, you may be asking whether this means 2 times e all raised to the x minus 1, or 2 times the quantity e to the x minus 1. And it's the understanding in algebra that if you raise something to a power and you multiply, if there are no parentheses, the exponent comes in before the 2. So in other words, the exponent is applied, and then afterwards I multiply by 2, and then I subtract 2 on the outside. So, so this is the way we interpret this expression. Okay, so when I go to draw this graph, I have to know something about the number e. And can anyone tell me what the value of e is approximately? Well, it's about 2.7. We said 2.718, but I think when we get down to locating points, I think 2.7 is close enough. And by the way, 1 over e, we said, is about 0.36, or what I use is roughly 1/3. This is about 1/3. So you want to keep these 2 values in mind. Let me add the 1/8 on there just to be a little bit more precise, but I don't think we'll be able to plot points with as much accuracy as to show hundredths and thousandths in the decimal expansion. And 1 over e, I'll be locating as roughly 1/3. Okay, so we said we're going to be lowering this graph 2 units. So if I lower the graph 2 units, I'll put in a horizontal line right here. This is the line y equals -2. And we said we were going to be shifting the graph 1 unit to the right, so my vertical axis is going to be shifted over 1 unit. Let's see, that was the x-axis, this is the y-axis, so this is the line, x equals 1. And so this is the point I would consider my new origin, is how we referred to it. This is the original origin, and now we're at the new origin. And what I'll be doing now is to double the altitude of every point because there's a stretch of 2. Okay, so at 0, I'd normally go up 1. Rather, at the origin, I'd normally go up 1. I'm going to go up 2 units because I've stretched it 2. And if I go to the right one, I would normally go up E. I'll go up twice that amount. Let's see, now E is about 2.7, so twice that's about 5.4. I'll go up a little bit over 5, between 5 and 6. 1, 2, 3, 4, 5, 6. Between 5 and 6, about halfway between, I'll go up to a point right about there. Now you might say, Dennis, exactly how high is that? Well, since I started 2 units below the original x-axis, this is actually at an altitude of 2e minus 2. 2e minus 2 is actually how high that value is right there. And going back to the origin, if I go over to the left one, I go up 1 over e, which we said was about 1/3, so I'll double it and go up about 2/3. Okay, so if I connect this point, and this point, my graph looks like this. And it approaches a horizontal asymptote, which is the x-axis after it's been shifted down 2 units. Okay, so this is the graph of f. So I might put a name tag on it right there. Okay, so that's how we go about sketching transformations of exponential functions. Let's go to episode 17 now and look at some of the review items for that episode. There were 2 formulas for compound interest that you should know and be able to apply on this exam. You know, we will return to the notion of compound interest later on when we get to one of the last episodes of this course, and we'll talk about annuities and how you figure the payment on a loan. So these 2 formulas are useful, but we'll see more information about this later on. If we come to the green screen, let me remind you what the formulas are. Okay, the first formula was A equals P times 1 plus R over N raised to the n t power. This is where P was the initial principal that was invested, whereas A is the amount in the account after a certain amount of time. R is the interest rate per year, but it's compounded n times per year, so you divide by n, and that figures the interest rate per period. And then you raise this to the number of periods power. So if t is the number of years, n periods in a year, then n times t is the number of periods. Okay, the other formula is for continuous compounding, in which we say A equals P e to the RT power. So this time with continuous compounding, you don't have periods as such, so there is no n, but this is the annual interest rate, and this is the number of years that the money is being compounded. So you should know these 2 formulas, and rather than working examples with these, I think our time's probably better spent going back to our list of items for episode 17 and seeing what other things you'll need to know here. So let's go back to episode 17. You should be able to convert between exponential and logarithmic expressions. Okay, well, let's see. Let's work an example of that. Suppose we said that 5 to the 3rd power is 125. We say that this is an exponential expression because we're using an exponent, and this is what most of us are accustomed to seeing. Rather than its logarithmic equivalent. Now the equivalent of this is to say log base 5 of 125 is equal to 3. Now if you have trouble remembering which numbers go where, remember that a logarithm is equal to an exponent. That was a fundamental fact that we've mentioned many times. So the exponent goes over here on the right. The logarithm is equal to 3. And the base 5 raised to the 3rd power, that's also the subscript on the log. And that leaves the numerical answer, 125, to go on the inside. This is sometimes referred to as the argument. So 5 to the 3rd power is equal to 125. Let's try doing this backwards. Suppose you were given a logarithmic expression like the log base b of a is equal to c. And I'm using letters here to try to disguise what their meaning might be. And so the question is, how could I write this in an exponential form? Anybody have an idea how you'd write that?
You could write it b to the c power equals a.
Okay, Tony, do you agree with that? Looks like you were going to give an answer too.
Yeah, that's what I was going to say.
Okay, so b to the c power is equal to a. Yeah, because here's base b, so that's going to be the base over here. C is the exponent because it's equal to the log, so c goes as a superscript. And then this is equal to a. So now we're converting from a logarithmic expression back to an exponential expression. Okay, back to our episode 17 list. You should be familiar with common and natural logarithmic expressions and how they're abbreviated. That is that base 10, or common logs, are abbreviated as log, and natural logarithms are abbreviated as ln for natural logarithms. It means base e. And remember that e is about 2.718 approximately. And then finally, you should be able to compute logarithmic values with a calculator. So here's a place where you'd want to use your calculator, as well as those compound interest formulas. I think you'd want to use your calculators. Though that item given at the very top there is a place where you'd want to use your calculator. So you should be able to find the natural log and the common log of numbers using your calculator. Okay, let's go to episode 18. And here we started getting into some more fundamental properties of logarithms, such as the 4 laws of logarithms. Now, you know, in a lot of textbooks, you'll find that they list more than 4 laws of logarithms, but I've tried to keep it abbreviated to only 4 logarithms to make them easier to apply. And many of the other laws that you see sometimes in textbooks are merely consequences of these 4. So let's come to the green screen and see what those 4 laws are. Let's see, the first law of logarithms says that if you take the log base, let's say base b, of a number m, plus the log base b of a number n, then you get what when you add those together?
Log base b of m times n.
Right, log base b of m times n. What do you think is the most common wrong answer that students put right here?
M plus n.
M plus n, yeah. See, when you see the addition of 2 logarithms, then it seems natural that you might want to be adding the m and n here. But it's actually a product, and the reason is a logarithm is an exponent. So what I'm doing is I'm adding 2 exponents. The exponent that you put on base b to get m, plus the exponent you put on base b to get m, is the exponent you put on base b to get mn. When you add 2 exponents, you get the exponent that belongs on the product. In the same way, the log base b of m minus the log base b of n. Tony, what do you think this one would be?
It's probably the log base b of m over n.
M over n, that's exactly right. And this time you see we're subtracting 2 exponents, that is we're subtracting 2 logarithms, and so what you get is the exponent that goes on the quotient. Now if necessary you can put parentheses around that to separate it, but sometimes putting in those parentheses makes it a little bit harder to read, I think. So you could either put parentheses on that quotient or not. Okay, the third law of exponents says that if you have the log base b of m to the c power, and I think I'll put parentheses on this one this time, then this c comes out. The exponent inside a logarithm comes out. But let's see, what will it be when I bring it out? Yeah, Tony.
It's c log base b.
Log base b of m, exactly, right. So this is c times that logarithm. If any parentheses are needed, I think maybe it would be right here. It's c times that logarithm. So what's surprising is if you have something in the exponent inside, it's not an exponent outside, it's a coefficient. And as a matter of fact, one of the common misinterpretations of the rule is to take a c on the outside, and when you bring it in, it's a coefficient rather than an exponent, but it should be an exponent, of course. So these laws are two-way streets. You can go either way with this. If there's an exponent inside, you can bring it out as a coefficient. If there's a coefficient outside, you can bring it in as an exponent. And the last rule is a little bit different, or the last law is a little bit different from the others, but it says if you have base b and you raise it to a logarithmic power, such as the log base b of m power, then you get m for the answer. And this is merely saying that a logarithm is an exponent. So what I've done is I place the logarithm in the exponential position where you'd normally expect to see an exponent. This is the exponent you'd put on base b if you wanted to get m for the answer. So look what we've done. We've placed it on base b, and so not surprising, we get m for the answer. Let me just ask you a couple questions right below here about these laws, and we'll keep these laws written up above. What would be the log base 5 of 3 plus the log base 5 of 7? Now, you know, I don't know what the log base 5 of 3 is or the log base 5 of 7 is, but there is a way that I could reduce this. Tony?
It'd be the log base 5 of 21.
Log base 5 of 21, exactly. Now, you notice these two bases have to be alike. If this had been base 5 and this had been base 3, then I wouldn't be able to combine them. They have to be the same base, and I get that base in the answer, but I get the product. Okay, very good. Another question might be, what is 1/2 the log base 9 of 81? Well, let's see. There are several ways I could work this, but I'm thinking let's use law number 3 that says if there's a coefficient, you can bring it in, but it'll be an exponent. So if I bring in the 1/2, how would I rewrite this as a logarithm with the 1/2 inside?
Log base 9 of 81 raised to the 1/2.
81 to the 1/2 power. Yeah, exactly. Now, what does the 1/2 power mean?
Square root.
Take a square root. So what I'll do is write this as a square root. That is the 1/2 power. Now, the square root of 81 is 9. So this is the log base 9 of 9. And what is the exponent I'd put on base 9 to get 9 for the answer?
1.
1. So this answer ends up being 1 in this case. This one I could actually reduce. Okay, one more problem that goes with these laws of logarithms. Suppose I had 6 raised to the 2 times log base 6 of 10 power. 6 raised to the power 2 log base 6 of 10. Well, now there's a base 6 here and there's a base 6 here, but what are we going to do with that 2 out in front? Tony?
We're going to put it as an exponent of 10.
Exactly. See, even up here in the exponent, I can move the 2 into the logarithm and it'll be an exponent. So this is 6 to the log base 6 of 10 squared, or 100. Right, so in other words, we just used law number 3 there. And now let's use law number 4 to reduce this ultimately. So what's the final answer going to be?
100.
Be 100, right, be 100. Because b to the log base b of m is m. 6 to the log base 6 of 100 is 100. So sometimes we're able to simplify these logarithms eventually, and sometimes we can merely we can simplify them but not give them a numerical value. Okay, let's go back to our list for episode 17. Know the 4 laws of logarithms, be able to apply these laws, and we just saw some examples of that. Know that logarithmic functions and exponential functions are inverses. Okay, now this is a fundamental property that's certainly important, and you'll get some sort of a question about this for sure, just like you will for those 4 laws we just went over when you're taking your test. So be prepared to know this next fact. Let's come to the green screen and discuss what that actually means. Suppose I have a function, f of x equals 5 to the x power. So this is an exponential function. And then there's a corresponding logarithmic function that is log base 5 of x. So I would refer to this as a logarithm function. And this exponential function is base 5, and this logarithmic function is base 5. Now, what's significant about the 2 functions is these are inverses of each other. You remember to say that a function is an inverse if this is the domain of a function f, and this is the range of a function f. We saw this not too long ago. Then if you take a number x in the domain of f and you send it over to a number y, which we might call f of x by way of f, then this is sort of the basic relationship here in a function. That is that every x is assigned to a unique y. Now, if this is a one-to-one function, I can reverse the process, and I can send this function, I can send the number y back to the x using the inverse function. And this becomes the domain of f inverse, the set on the right, and the set on the left becomes the range of f inverse. And so what happens is if you start off with x, and if you send x away by f, and then afterwards you apply f inverse, you come right back. And we would summarize this by saying that f inverse of f of x is x. Because you start with x, f sends it away, f inverse brings it back, and you're right back where you started. Now this is sometimes written as a composition of functions in this form. Now the same thing holds true if I had chosen my x over here in the domain of f inverse. F inverse could send it away, and then f could send it back afterwards, and I'd come right back where I started. You notice this x is actually different than that x because this x is chosen in the set on the right, not the set on the left. And in that case, I would say that f composed with f inverse of x is equal to x. Now, this is only going to be the case for functions and their inverses. And let's see if that's the case with the two functions we have at the top of our screen here. So the way I'm going to find out if these two functions are really inverses of each other is I'm going to take their composition. Let's try taking the composition f inverse composed with f of x. Oh, except that I better call it g here, I guess, not f inverse. We don't know it's the inverse function yet. So I'm going to take the composition of g with f. Now, the way we interpret this is g of f of x. And f of x is 5 to the x. So this is 5 to the x power. And now what does g do to that? G takes the logarithm of any number that you put inside of g. So if I put in an x, I get the log base 5 of x. If I have 5 to the x, what I get is the log base 5 of the quantity 5 to the x. Now you might say, well, Dennis, this doesn't look like x. I thought you said the composition was going to give you x. Well, let's see what happens if I reduce it. If I bring the exponent out in front, then I get the log base 5 of 5. And the log base 5 of 5 is 1, so this is x times 1 is x. Yes, and so we're all excited here because we've started off with x and I got x when I finished. Now, if I work this in the reverse order, I don't think I'll work this one out, but I'll leave this one for you to check. If I work this in the reverse order, I will eventually get x again. So what that tells me is these are inverse functions of one another, and that's going to help me draw graphs of these functions coming up. Now, this also explains, I think, why exponential and logarithmic functions are discussed in this chapter and or together for this exam is because they're related to each other. They're inverses of one another. Okay, let's go back to our episode 18 list. Be able to graph logarithm functions. Well, now that's a consequence of what we've just been over right here. Let's see how we'd go about graphing the log base 5 of x, for example. Let's see, we just had g of x equals the log base 5 of x. And I want to be able to graph that. So what I'm going to do is keep in mind how I would graph its inverse function, 5 to the x. So let's sketch our graph right here. Okay, so what I want to do is to graph the function g, but I'm going to be keeping in mind what the graph of the function f looks like. You remember to graph this exponential function, at the origin, we started off and we went up 1. Well, for the inverse function, I'm going to be flipping this over the 45-degree line. I'm going to be flipping that over, and instead of going up 1, I'm going to go to the right 1. And for the exponential function, if I went to the right 1, I'd go up 5. So now, when I flip it over, if I go up 1, I'll go over 5. And for the original exponential function, if I went to the left -1, I went up the reciprocal of the base. So now, when I flip it, if I go down 1, I go over the reciprocal of the base, or 1/5. And I get a graph that looks like this. And it approaches a vertical asymptote at the y-axis. So this is the graph of g of x equals the log base 5 of x. You know, one of the characteristics of fundamental logarithmic functions is they all cross the x-axis at 1. They have an x-intercept, but they have no y-intercepts. And a fundamental characteristic of the exponential functions is they all cross the y-axis at 1, and they have no x-intercept. So you see, everything's been reversed because of this inverse relationship. Let's try sketching a transformation of a logarithm function while we're at it. For example, suppose I wanted to graph the function f of t equals the log base 2 of x plus 3 plus 1. Well, basically, we're graphing, well, I should put a t in there, shouldn't I, because I said f of t. So basically, we're graphing the function f of t equals the log base 2 of t, but there are two changes being made in this graph. The plus 1 here causes the graph to do what?
Move up 1?
Yeah, it's going to move up 1. Thank you. Right, it's going to move up 1. And the t plus 3 is going to shift the graph in which way?
To the left.
It's going to move it to the left 3. Okay. And I think those are the only changes we're going to be making in this fundamental function. There's no negative in front, so we're not going to flip it over. There's no other coefficient in front that's going to cause a stretch or a compression. So if we set up our coordinate system, let's see, we said we're going to raise the graph 1 unit. So when I go up 1, that's going to make this point at 1 my new origin, except I still have to shift it over 3. And my vertical asymptote is going to move over 3 units. I'll put a dotted line in right here. This would be at t equals -3, because this is the t-axis and the y-axis. So that says that right here, that's at -3 plus 1. This is my new origin. And from my new origin, I should go to the right 1. And if I go up 1, I should go over 2. And if I go down 1, I should go over 1/2. So here are my 3 target points. And on this basis, I can sketch the graph. Yep, and so this is the graph of capital F. Now, when you graph these functions, you should plot only the target points and not make a table of values. Now, you might say, well, Dennis, what's wrong with making a table of values? Well, you see, what we're trying to do is to graph these by speed and not necessarily accuracy. If I plotted more points, I could get a more accurate graph, but I'll never get a truly accurate graph because I just can't plot all the points that the graph goes through. So we try to have a minimal number of points that we can plot. And so we plot only these 3 target points, and this is what we'll be looking for when we grade your exam. So don't plot more points, don't make a table of values, but just know how to plot these 3. You should be familiar enough with those points based on our previous discussions and the homework that you've been doing. Okay, so those were transformations of logarithm graphs. And there are only 3 new graphs that we talk about in this course. Those are the conic sections that will come up later on. Okay, let's go to episode 18. Excuse me, I'm sorry. We want to go to episode 19. Okay, we want to be able to solve exponential and logarithmic equations. And there are quite a variety of these. Let's just take a few examples to kind of remind you what they might look like. Now, first of all, let's take a problem that you can solve, that you could have solved actually before you took this course. That's an exponential equation. So if you come to the green screen, suppose we had 7 raised to the x minus 3 power equals 49. Now, this is an equation because I have 2 quantities equal with a variable in it. And because there's an exponential expression in it, I'll call this an exponential equation. But that doesn't make it difficult to solve. This one's actually fairly straightforward. I think what we have to recognize is that on each side, I can find an expression with a base 7. 7 to the x minus 3, and over here, 7 squared. So 7 to this power equals 7 to this power. So what's the natural conclusion that we're going to draw here?
X equals 5.
Well, okay, that is going to be the answer, but what I'm thinking is I know that this exponent should equal 2. So x minus 3 equals 2. And you see what's significant here is this is now a linear equation. It's like the most fundamental equation that we could solve. So I no longer have an exponential equation, I have a linear equation. And if I solve it, Tony says x will equal 5. That's exactly right. So here's our solution. And we found it by actually changing the problem into a simpler form and then solving that. So x is equal to 5 here. Let's just check that. If I substitute in a 5 right there, then I'm going to have 7 to the 5 minus 3 power. That's 7 squared. 7 squared is 49. That's right. Okay, now let's take a problem that's maybe not quite that easy to solve, but it's still an exponential equation. And for this next one, we'll be using a calculator. Suppose we had 10 to the 2x plus 1 power is equal to, let's say, 74 is equal to 74. Well, you see, the problem now is I have a base 10 here, but I don't see any way I could make that a base 10. I don't see any way I could make these have a common base. So now I'm going to have to solve this exponential equation, but what I'll be doing is applying logarithms. So I'm going to take advantage of the fact that exponential functions and logarithmic functions are inverses of each other. I should take a log on both sides. Now, you know, technically I could use any base I wish. But what do you think would be the most natural base to, maybe natural is the wrong word to use here. What do you think would be the most appropriate base to use?
Maybe 2.
Well, not 2, but since there's a base 10 here, and I have base 10 on my calculator, I think I'll use base 10, or a common logarithm. Base 2 might seem appropriate because these both have a factor of 2 in them, but I think since I have base 10 on my calculator, I'll use that. So log base 10 of 10 to the 2x plus 1 equals the log base 10 of 74. Now, why am I not writing a subscript on these logarithms?
Because if you don't write a log, or if you don't write a subscript, it's just assumed that it's 10.
Yeah, if you don't write a subscript, it's assumed to be 10. Now, you know, I should give you a bit of warning here. If you're going to take more mathematics and science courses, there are some later textbooks that will write log to mean a natural logarithm as opposed to ln. You remember ln means a natural logarithm in our course? So you have to be kind of careful. In some more advanced math courses, the natural log is used so commonly that when they write log, they mean base e. But we'll be assuming that log means base 10. This is the way it would be written on your calculator. Now, I'm going to use a property of logarithms to bring the exponent out in front. 2x plus 1 times log 10 equals the log of 74. And what is the log of 10?
1.
Is 1. Yeah, this number is just a 1. Because remember, a logarithm's an exponent. What's the exponent you'd put on this base to get this answer? Well, you'd put exponent 1 on base 10 to get a 10 for the answer. So that's 1. So this tells me that 2x plus 1 is equal to the log of 74. Now, I could calculate this on my calculator, but rather than doing that yet, I want to get the exact answer. I'm going to solve for x. 2x is equal to the log of 74 minus 1. And then I'm going to divide by 2, and I have the log of 74 minus 1 all over 2. Now, I would call this the exact answer. And you see what I did to get to arrive at that is I solved this linear equation that I had in the middle. This is a linear equation even though it may not look linear because of this expression, but this is merely a number. So 2x plus 1 is equal to this other number, and I isolated the x. Now, of course, most people would want to approximate that to find out roughly how much that is. So if I go to my calculator, I'll find out how much this expression will be. If we can zoom in on my calculator right here. And here's one of those places where on the exam you might want to have a calculator available to you. So I'm going to take the log of 74. Let's see, the log of 74 minus 1. Oops, excuse me, minus 1. And I'm going to total that up and then divide by 2. So that's the log of 74 minus 1. Now divide that by 2. And I get 0.43. Let's round that off. 435. I'm going to round that off to 3 decimal places, 0.435. So I'll write that as 0.435. Okay, now I was using a TI-82 to work that problem. Now let's go to a different calculator and just see how the difference in the keys will be. So, okay, now one of the differences here is that the order of the key usage is going to change just a little bit. So this is a TI-30, and let's see how the problem will be solved here. Now, to find the log of 74, I'm first going to enter 74 and then push the log button. And then I'm going to subtract 1 equals. Okay, and then afterwards I divide by 2. And you see when I round this off to 3 decimal places, it'll be 0.435. So that's exactly the same number that we calculated on the other calculator. By the way, while we're at it, I might point out that occasionally on 2 different calculators, this last digit will be slightly different. Like on another calculator, you could see a 158 instead of a 159. That's because all of these logarithmic values are approximated using formulas that are embedded within the calculator. And some of the formulas are abbreviated depending on the power of the calculator. And it will sometimes cause that last digit to change. So you never know if you see 2 different calculators with a different digit on the end, which one is correct, if either one of them is correct. But those digits have all been rounded off, the last digit, according to the program that they have stored in them. The same thing holds for square roots and cube roots and for exponential values. Okay, well, you can see, well, the answer that we just calculated, 0.435, is the same on both calculators. Okay, now, those are 2 examples of exponential equations. Now, there is a formula I don't think I've mentioned yet today that you need to be aware of, and that's the change of base formula. So let's go to the green screen, and let me just remind you how that goes. For example, suppose you wanted to find the log base 2 of 7, but you go to your calculator, you don't have a log base 2 button. So what you would do is use the change of base formula that says you can write log 7 using any other base, say base 10, log 7, but then you have to divide by that same logarithmic base of the old base 2. So the log of 7 divided by the log of 2. Another way to write this would be to say take the natural log of 7. That's log base e, 2.7 approximately. But then you have to divide by the natural log of the old base 2. And on our calculator, we have an LOG button and we have a natural log, LN button. Those are the only 2 they've given us, but we don't have a log base 2 button. So if you wanted to find this logarithm with this base 2, you'd have to convert it using the change of base formula to either common logs or natural logs. Okay, I don't think I mentioned that in earlier today, but you certainly want to know that formula as well. Okay, now let's try solving a logarithmic equation. And suppose the equation were something like this. Let's say we have the log base 3 of x minus the log base 3 of x plus 1 is equal to 2. Now, here I have an equation, but I have logarithms involved in it rather than exponentials, so I would refer to this as a logarithmic equation. And when you see a problem, something like this on the exam, what you should do is combine the logarithms together. So I'm going to write this as a single logarithm, log base 3 of, now let's see, I've subtracted 2 logarithms. So that'll be the log of the, what do I put here?
You put x over x plus 1.
X over x plus 1, right. That was using our second law of logarithms that we saw earlier. So the log base 3 of this expression is equal to 2. Now I'm going to change this to exponential form, that by removing the logarithm and saying 3 raised to the second power is equal to the quantity inside. 3 to the second power equals x over x plus 1. Okay, well now what I have is a rational equation, because I have a rational expression and I have this ratio. So this is a rational equation. And I'd like to solve that. Well, this says 9 is equal to x over x plus 1. And let's multiply both sides of x plus 1, and that'll be 9 times x plus 1 is equal to x. Well, you know, I no longer have a ratio. This is a linear equation. So I'm slowly getting this down to a form that I'd like to solve. And I think this one we can work with. This says 9x plus 9 is equal to x. Or that says that 8x is equal to negative 9. And that says that x is equal to negative 9 over 8. Negative 9 over 8. So therefore, do you think that this is the solution to that problem? Well, you would think so, but you know what? We have to throw this one out, and we have to say that there's no solution. Now, why is that?
You can't take the log of a negative number.
Yeah, you see, back here, there was an assumption that we were making about x. You can't take the log of a negative number. You remember logarithm graphs have this general shape? We said that they cross at 1. And therefore, when you take a logarithm, you can't take a log of a negative number because there's no graph over here. So we were assuming all along that x was bigger than 0. And I was also assuming that x plus 1 was bigger than 0. Well, it turns out if x is bigger than 0, x plus 1 has to be bigger than 0. So this really wasn't of any consequence in this problem. So if I come up with any number that with any number down here that is negative, I have to throw it away. It's a solution of the rational equation, and it's a solution of all the linear equations all the way down, but it wasn't a solution of the original logarithmic equation. Now you might say, Dennis, would it have been a solution of this one? Turns out it would have been, because if you had substituted in negative 9 over 8, you would have had a negative in the numerator and a negative in the denominator, and that ratio would have been positive, and I could have proceeded from here. So it's actually a solution of this equation. But it's not a solution of the original equation where the two logs had been separated. So this problem has no answer. Okay, let's take another example. Okay, let's try solving this problem. It says 2 log x equals log 2 plus log of, let's say, 3x minus 4. Okay, so this time I have logarithms in 3 different expressions. So as a general rule, I would say get all the logarithms on one side. Now, in this case, you could actually leave the log of 2 separated from the other logs because it has no variable in it. But just to kind of keep things in the same order, I want to get all the logs on one side. So I'm going to move these two guys over here to the left. 2 log x minus log 2 minus log 3x minus 4 equals 0. Now, when I get all the logs on one side, then the idea is to combine them. Well, let's see, I've got a coefficient on this one, and I didn't on either of the others. What can I do with the coefficient?
Change it to log x squared.
Log x squared. Okay, so let's write this one more time as the log of x squared minus the log of 2 minus the log of 3x minus 4 equals 0. Okay, so I have a logarithm. I'm subtracting this one, and I'm subtracting this one. That says I should write this as a quotient inside a logarithm, and both of these will be in the denominator because they've both been subtracted. So I'll write this as the log of x squared divided by, now let's see, I'll have to put a 2 in the denominator, and I'll have to put the 3x minus 4 in the denominator, and this is equal to 0. Okay, so this is a base 10 log, and 10 to the 0 power, which is 1, 10 to the 0 power is 1, is equal to this expression. So this tells me that x squared over 2 times 3x minus 4 is equal to 10 to the 0 power, and we said that was equal to 1. So if I multiply both sides by 2 times 3x minus 4, this says that x squared is equal to 2 times 3x minus 4 times 1, but we don't need to bother showing the times 1. What kind of an equation do I have here? This isn't a linear equation. What is
Quadratic.
that? It's a quadratic equation, yeah. So I had logarithmic equations, I had a rational equation, and now I have a quadratic equation. Okay, so you just never know what's going to come up as you reduce these, but I think we're in better shape than when we had logs in there. So to solve this, I'm going to multiply that out. Let me just draw a line here. That's going to say x squared is equal to 6x minus 8. How would you go about solving that?
Move everything over to one side.
Move everything on one side. Let's keep the x squared positive, so I'll move everything to the left. X squared minus 6x plus 8 equals 0. Now, we could use the quadratic formula to solve this, but there's a faster way, and what is that? Tony, what would you say? Jeff, what would you say?
I'm not sure.
Complete the square.
We could complete the square, but there's even a better way yet. How about factoring? Let's see if this will factor. If we can factor it, that's usually the quickest way out of these things. There's an x squared, so I know I have to put an x in front of each of these. There's a plus on the 8. That tells me the signs are alike. And there's a negative, so something's negative. If the signs are alike, they must both be negative. So now I'm looking for two numbers to fill in here that will give me that quadratic. What should they be?
2 and
2 and 4, right. Very good, 2 and 4. So either x minus 2 is 0 or x minus 4 is 0. Now I tell you what, if x minus 2 is 0, I'm running out of room. What would x have to be?
2.
2, okay. And the other one, if x minus 4 was 0, x would be 4. Now, do all these numbers make sense? Because you see, we may have to throw one of these roots out like we did before. Let's take the 2. If I substitute the 2 back here, log 2, that's okay. Log 2, well, that one's constant there. And this would, if I plug in a 2, that'll be the log of 2. As a matter of fact, I think you can see this says 2 times the log of 2 is the log of 2 plus the log of 2. Yeah, that would be 2 times the log of 2. This one certainly checks, and it's just fine. How about the 4? 2 times the log of 4 equals the log of 2 plus the log of, how much will that number be when you plug in a 4? 12 minus 4 is 8. Yeah, 12 minus 4 is 8. But I don't see any negatives coming up inside the logarithm, so this number should check that problem. If you work that out, those two sides should be equal. So both of these numbers are, shall we say, keepers. If I had to throw one out, the term they use for that is an extraneous root. But this time we don't have an extraneous root. We did have an extraneous root in that last problem that we worked though. Okay, let's go to episode 20 and look at applications of exponentials and logarithms. And first of all, let me point out that in the episodes that we've just finished recently in the last few days, we talked about the pH of a solution. We talked about the decibel level of sound. We talked about the Richter scale. I'm not going to ask you about any of those on the exam, so you don't need to know those formulas, and I won't be asking you about those, primarily because we didn't spend a lot of time on that. So what I will ask you about are things like what you see here. You should be able to solve problems that deal with population growth, radioactive decay, and Newton's law of cooling. Now, in the few minutes that we have left, let's take a problem like, let's say, radioactive decay. Suppose I have some material, like a blob of material here, and let's say this is radioactive. Don't be scared, this is only an example. Okay, let's say this is radioactive, and what if we have 4 grams of radioactive material? This could be uranium or some other radioactive element. Now suppose this material has a half-life of, let's see, let's don't make the half-life too long. What should we pick? Half-life of, let's say in days. How many days?
7.
7 days, okay. 7 days, 1 week, okay. That's the half-life, 7 days. So in other words, if at this moment I have 4 grams of the radioactive material, 7 days later, how much of this will still be radioactive?
2 grams.
2 grams. Half of it has become a stable element. The other half is still radioactive. And after another week, how much of this will be radioactive?
1 gram.
1 gram, because every time half of the remaining material becomes stable and half is still radioactive. So we might ask this question, how much of this material, that is these 4 grams, is radioactive after, let's say, 23 days. 23 days, because I want to pick a number that's not just a multiple of 7. Otherwise, I think we could work it out without much difficulty. Okay, so our formula is this. The amount of radioactive material at time t is equal to the initial amount of radioactive material times e to the RT power, where R is the rate of radioactive decay. Okay, well, the initial amount is 4, so I know that A of T is equal to 4 e to the RT. And I know that the half-life is 7 days, so I know that after 7 days, A at 7 will be 2.
Isn't the rate? Isn't R supposed to be? Isn't it?
Oh, you're right.
Negative?
I should have put a negative on there. Thank you very much. I should put a negative on there because this is radioactive decay, so this is decreasing. And that'll be 4e to the negative R times 7. You see, I'm plugging in a 7 for T, so I have to put a 7 right here. So I want to solve for R. And that says that 1/2 is equal to e to the negative 7r. And then I'll take a natural log of each side, so I get ln of 1/2 equals negative 7r. What I've done is I have brought the negative 7r out in front, and the natural log of e is 1. So this says that r is equal to negative 1/7 ln of 1/2. So if I want to find out how much is left after 23 days, I'll have to compute A at 23, and that's going to be 4 times E to the negative R power. Let's see, now I already have a negative on that, so the negative R power is the 1/7 ln 1/2 times T, which is 4 times 1/2 to the T over, oops, that should be 23 for T. We'll put a 23 right there. 23 over 3. See, if I put 23 here, I have to put 23 in over 7. Okay, now I think I'm just about out of time, but if you multiply this out on your calculator, you'll have the number of grams of material that's radioactive after 23 days. Well, I will see you next time for episode 28. This is episode 21 of MATH1050 College Algebra for our television course. I'm Dennis Allison, and I teach in the math department. We'll be looking at a review today of the chapter on logarithms and exponential functions. Let's go to our first list of review ideas. Number one, you want to be prepared to solve problems that are similar to those that we've just been discussing in class in the last few episodes, and those assigned for homework. Now, you know, occasionally there have been some problems that we didn't necessarily later. To find an exponential value, you'll either have a key that says y to the x, or it could say x to the y. This depends on the manufacturer of your calculator. Or another common exponential key is this little caret thing pointing up. And you enter the base, then you push this button, one of these buttons, and then you push your exponent afterwards, and then you hit the equal sign or the enter sign, and you'll get the exponential. So for example, if you want to say 2 to the third power, then you hit the equal sign, and it should say 8. Now, of course, the reason you hit the equal sign is because when you hit 3, when you push 3, your calculator doesn't know if you're pausing to enter 31, 2 to the 31 power, or if you're finished. So when you hit the equal sign or the enter sign, then the calculator knows that you're done. Okay, let's go back to episode 16 and look at the other items on that list. You should be able to sketch the fundamental exponential functions, and then in connection with first power is 4, so I went up 4. And when x was -1, then the value there is 4 to the negative 1 power, and 4 to the negative 1 is 1/4. So we went up the reciprocal of the base. Now, on the basis of only those 3 target points, we can draw our exponential graph, but we have to know that there's a horizontal asymptote along the x-axis, and we have to know that there is no vertical asymptote, so I don't draw in any vertical dotted lines. So this is how we'd like for you to graph this function and not make a table of other values, but plot only these three points. Let's take one more example of an exponential function. And I'm going to try to hide it in a sort of a minimal way. Let's say we call this function g of x. And let's say this function is 3 to the negative x power. What is the effect of the negative in the exponent? What is that done to hide the exponential function? Cover in our television course, but you'll find examples like those in the textbook. You want to make sure you know how to do those. One of the differences between this exam and the first 2 exams is you can use a calculator to solve certain problems. Those problems will be given to you separately on the test, so that you should be able to use your calculator to compute logarithmic values as we encounter them. You cannot use notes, and of course you cannot use your textbook. You'll be given some extra scratch paper with the exam, but you'll have to turn that in when you turn in your exam. And we encourage you to show all your work to justify your answers. Otherwise, if you have a wrong answer, you may lose full credit. Whereas if you show some work, then if we can find the mistake that you might make in that, then you can get partial credit. And we try to be fairly generous with the partial credit. Okay, let's look at the review ideas for episode 16. Now, in episode 16, we introduced exponential values and how to compute those with your calculator. Now, if we can come back to the green screen, let me just remind you that on your calculator, you should be able to sketch transformations of those functions. And in each case, this should be done by plotting only the target points, not making a table of values. Why don't we take a few examples of those right here? Suppose that I wanted to graph the function f of x equals 4 to the x power. Then there were 3 target points that we associate with this exponential function. And let's see, let's just get our graph system, our coordinate system set up here. And the target points were, let's see, now at 0 we go up 1 unit. And if I go over 1 from the origin, then I should go up whatever the base is. So I go up 4. So I'm going up 4 right there. And if I go to the left 1, I go up the reciprocal of the base, 1/4. Now, you notice I'm doing this in a rather mechanical way, but I think all of these values make sense because you see when I choose x to be 0, when x is 0, I get 4 to the 0 or 1. When I choose x to be 1 right here, then when x is 1, 4 to the